So in this lecture we will be discussing about design of beams for flexure by using IS 456 2000 and SP16 methods. First we will take up a design of singly reinforced beam. So my design stipulations are, so beam size 200 into 500 mm. So here width of the beam, it is 200 millimeter. Overall depth it is 500 millimeter, and grade of concrete FCK, it is 25 Newton per mm square. I will be using M25 grade of concrete. And FY grade of steel, it is 500 Newton per mm square. So this is M20 grade concrete, sorry M25. M25 grade concrete, and steel will be FE 500. And clear cover for beams, it is 25 millimeter. So this clear cover, it is 25 millimeter. And my analysis moment from ETAPS at ultimate load combinations, so it is MU 130 kilonewton meter. So I will convert this to Newton millimeter. So it will be 130 into 10 power 6 Newton millimeter. So this is my analysis moment. Analysis moment from ETAPS. At ultimate load combination. So ultimate load combination will be 1.5 times dead load plus 1.5 times live load. So I will be using longitudinal bars, of 12 mm dia, and stirrup diameter 8 mm. So initially I will assume I will provide single layer of reinforcement. Okay. So let me calculate the effective depth. So in this case, effective depth will be, so overall depth it is 500 minus clear cover 25 plus diameter of shear reinforcement bars, it is 8 mm, plus diameter of longitudinal bar divided by 2. So longitudinal bar diameter 12 divided by 2. So this is 12 divided by 2. So let me calculate the effective depth. So it is 500 minus 25 plus 8 plus, so again 12 by 2, it is 6. So 461 461 millimeter. So this effective depth it is 461 millimeter. So now let me calculate the moment capacity of the beam. So it can be calculated as mu limit equals 0.133 FCK BD square. So 0.133, your FCK will be 25, width of the section it is 200, again effective depth it is 461 square. So let me solve this. 0.133 into 25 into 200 into 461. So it will be 141326465. So it is in Newton millimeter. So if you divide this value by 10 power 6, so then it will be get converted to kilonewton meters. So divided by 1 into 10 power 6. So it is 141.32. 141.32. So it is nearly equal to 142 kilonewton meter. So this is mu limit. So which is nothing but capacity of section. In the next step, you compare mu limit and mu. So here mu limit is 142 kilonewton meter and mu it is 130 kilonewton meter. So 142 is your capacity of section. So 130 is your analysis moment. Analysis moment. So in this case, mu is greater than mu limit is greater than mu, which means capacity of section which is much more higher than your analysis moment. So in this case, it is treated as the section is singly reinforced section. The section is singly reinforced section. What it means? If the reinforcement is provided only in tension zone, it is called a singly reinforced beam. Okay. Next, let me calculate the area of steel. So to calculate the area of steel, we will be using this formula. AST equals 0.5 FCK divided by Fy into 1 minus square root of again 1 minus 4.6 into mu divided by FCK BD square into BD. So this is the formula to calculate the area of steel. So let me substitute all the values. So 0.5, your grade of concrete, it is 25, grade of steel 500 into 1 minus square root of, again 1 minus 4.6 mu. It is your analysis moment. So 130 into 10 power 6 divided by, again FCK, grade of concrete 25, into width of the beam 200, effective depth it is 461 square. 461 square multiplied by width of the section 200, again effective depth 461. So let me calculate the area of steel. So first it is 0.5 into 25 divided by 500. 1 minus square root of, again 1 minus 4.6 into 130 into 10 power 6. So divided by 25 into 200 into 461 square. 461 square into 200 into 461. So it is 780. So area of steel, it is 780 mm square. So this is area of steel required. It is area of steel required. Now I will convert this area of steel to number of bars. So number of bars equals 780 divided by, so I will go with the 12 mm dia bars. So area of 12 mm dia bar, it is pi into 12 square divided by 4. So it is 780 divided by pi into 12 square divided by 4. It is 6.89. 6.89. So I will round off to 8 numbers. Clear? So I need 12 mm dia bars, 8 numbers. Your beam width is 200 mm. Will it be possible to accommodate 8 number of bars in 200 mm width? So it is highly impossible. So for which to match this area of steel. So what is the area of steel required? 780 mm square. To match this reinforcement, I will provide the area of steel. In 2 layers. So first layer, 3 bars of 16 mm dia. In the second layer, 2 bars of 12 mm dia. So 3 bars of 16 mm. So area of 116 mm dia bar. So it is pi into 16 square divided by 4 plus here 2 into pi into 12 square divided by 4. So first 2 into pi into 16 square divided by 4 plus, sorry, it is 3 numbers. So 3 into, next 2 into pi into 12 square divided by 4. So it will be 829. So nearly it is equal to 830 mm square. So AST provided it is 830 mm square. So my requirement AST required, it is 780 mm square. So initially I assumed to provide reinforcement in single layer, but at the end I will end up by providing the reinforcement in two layers. While providing single layer of reinforcement, so your effective depth will be 461 millimeter. For 461 you need a steel of 780 mm square, but you decided to provide reinforcement in two layers. So if you are adopting two layer of reinforcement, what is the effective depth? So effective depth will be 500 minus 25 plus 8 plus your first layer of bar 16 mm dia, second layer bars are 12 mm, 12 by 2. So your effective depth will be reduced. So 500 minus 25 plus 8 plus 16 plus 12 by 2, it is 6. So it will be 445 mm. So your effective depth, it is 445 mm. So this is when we are using single layer. So this is when we use two layer of reinforcement. So effective depth get decreased to 445. Initially it was 461. It get decreased to 445. So for 461 you need a steel of 780. Then what is the steel requirement for 445? So again you use the same equation. AST equals 0.5, FCK is 25, Fy it is 500 multiplied by 1 minus again 1 minus 4.6 into mu. Mu is 130 into 10 power 6 divided by your FCK 25, width of the section 200, your effective depth, it is 445 square. So into 200 into 445. So let me calculate the area of steel. So it is 0.5 into 25 divided by 500 multiplied by 1 minus square root of, again 1 minus 4.6 into 130 into 10 power 6 divided by 25 into 200 into 445 square. So into 200 into 445. So you need 824. So AST equals 825 mm square. So when your effective depth is 461, you need a steel of 780. When your effective depth is 445, you need a steel of 825 mm square. Okay. So my area of steel required now it is 825 mm square. So AST required, it is 825 mm square. So I will provide again 2 layer of reinforcement, 3 bars of 16 mm. In first layer. In second layer, 2 bars of 12 mm dia. So if you calculate the area of steel for this arrangement, so if you calculate the area of steel for this arrangement, so it will be around 830 mm square. So you need a steel of 825, you are providing 830. So here AST provided, which is greater than your requirement, area of steel requirement. So hence it is okay. Okay. So what is the percentage steel you provided? So you convert this AST to percentage of steel PT. So you have a formula, percentage of steel PT equals AST multiplied by 100 divided by B into D. So your area of steel, it is 830 you provided, multiplied by 100 divided by your width of the section 200, again multiplied by D, it is 445. So percentage of steel PT, 830 multiplied by 100 divided by 200 into 445. So it is 0.93%. 0.93%. It is the percentage of steel provided. So you need to check whether PT provided, it will satisfy the maximum requirement. It should be less than PT limiting percentage of steel. Then your section will be under reinforced. Yeah, then your section will be under reinforced. How to check whether PT provided which is less than maximum percentage? So for which you need to refer table E of SP16. I think it's in page number 10. So let me open SP16. So page number 10. Yes, it is in page number 10. So table E, maximum percentage of tensile reinforcement PT limit for singly reinforced sections. So you have grade of concrete M25 and grade of steel 500, for which limiting percentage of steel is 0.94. So 0.94. So here you provided a steel of 0.93%, which is less than your maximum limit. So maximum limit is 0.94%. So then you can say your section is under reinforced. Okay. So how to detail this beam? So this is your detailing part. So these are your first layer bars, 3 bars of 16 mm dia. Next, in the second layer we will be using only 2. So you remove this. So you will be using 2 bars of 12 mm dia, and these 2 are your compression reinforcement. So minimum you should have 2 bars of 12 mm dia. 12 mm dia. So next you need to check. So you need to check minimum clearance between individual bars. So for which you need to refer IS 456 2000, page number 45, that is clause 26.3.2. So you provided 3 bars of 16 mm dia. So then you need to check what is the distance between individual bars. Okay, so let me open the code. So IS 456, page number 45. See, clause 26.3.2, minimum distance between individual bars. The horizontal distance between 2 parallel main reinforcing bars shall usually be not less than the greatest of the following. So first case is the diameter of the bar if the diameters are equal. So first condition it is diameter of the bar. So first layer is 16 mm, second layer is 12 mm. So absolutely it is 16. Next, second criteria, the diameter of the larger bar if the diameters are unequal. So again it will be 16 mm. Next, third criteria, 5 mm more than the nominal size of coarse aggregate. So 5 mm more than the nominal size of coarse aggregate. So 5 plus, so coarse aggregate size is 20 mm. So it will be 25 mm. So you have 3 criteria. So out of 3 you need to provide whichever is greater. So among these 3, the greater value it is 25 mm, which means you need to maintain the distance, minimum clearance between the individual bars as 25 mm. Minimum you should have a 25 mm. These two distance. You should not place a bars less than 25 mm distance. So this is as per IS 456. So if you refer SP 34 and page number 99, clause 8.2, clause 8.2, you have the same criteria. You have the same criteria for minimum clearance between individual bars. Either you can refer IS 456 or you can refer SP 34. Okay. So as per the code, minimum clearance between individual bars, it should be 25 mm. So now we shall calculate the actual distance. So how to calculate the actual distance? So you have a beam width of 200 minus, on both sides you have a clear cover of 25 mm, and you are using two-legged stirrup, 8 plus 8, plus you have 3 bars of 16 mm dia. Okay. So 200 minus 25 plus 25 plus 8 plus 8. So again it will be 3 into 16. So it is 86 mm. So total this distance is 86 mm. Here you have two spacing. So I will remove this. Here if you observe, you have two spacing. So this is your first spacing and this is your second spacing. So 86 divided by 2. So 86 divided by 2, I think you will be getting 43 mm. The code says minimum clearance between the individual bars, it should be 25 mm, but actually I have a distance of 43 mm. Okay, so here it is 43 mm, which is greater than 25 mm. So hence it is okay. So this check, it has been passed. Minimum clearance between individual bars. So as you are using two layer of reinforcement, again you should check minimum vertical distance between bars. So vertical distance is this one in vertical direction. Initially you calculated the horizontal distance. Now you need to check the vertical distance between the bars. So second check will be minimum vertical distance between bars. So for which you need to refer IS 456 2000, same page number 45, I think 46 also, clause same 26.3.2. So let me check the code. So this is the clause 26.3.2. In the same clause it has been continued on page number 46. See here, where there are two or more rows of bars, the bars shall be vertically in line and the minimum vertical distance between the bars shall be 15 mm. So first criteria it is you should maintain a vertical distance of 15 mm. Second criteria, 2/3 the nominal maximum size of aggregate. So second criteria it will be 2 by 3 times 20 mm size aggregate. I think it will be 13.3 millimeter. So third criteria. So third criteria, the maximum size of bars. Here maximum size of bars is 16 mm. Again code says whichever is greater. So among these three values you need to provide whichever is greater. So among three values, so greater value it is 16 mm. It is 16 mm. So which means the distance or the gap between the two layers you should have a 16 mm. So for horizontal distance minimum you should have 25 mm. So again this clause, same clause it is in SP34 page number 100. So this is how you can check minimum horizontal distance between individual bars and minimum vertical distance between bars. Okay. So AST provided. So what is the area of steel you provided? I think it is 830 mm square. Area of steel provided it is 830 mm square. Again you need to check minimum and maximum tension for tension reinforcement. So minimum tension reinforcement, minimum tension reinforcement, so for which you need to refer IS 456 2000. So clause 26.5.1.1 and page number 47. So page number 47. See here. Yes. Minimum reinforcement. The minimum area of tension reinforcement shall be not less than that AS divided by BD equals 0.85 divided by Fy. So here AS is minimum area of tension reinforcement, B is width of the section, D is effective depth and Fy is your grade of steel. So what is the formula? AST divided by BD equals 0.85 divided by Fy. So let me calculate the minimum requirement. So AST minimum. So AST minimum, which is equal to 0.85 multiplied by 200 multiplied by effective depth, it is 445, divided by your grade of steel, it is 500. So let me solve this. So 0.85 multiplied by 200 multiplied by 445, again divided by 500. So you required a minimum steel of 151.3. So it is 152. So this is your AST minimum requirement. So what is the maximum requirement? So next, maximum tension reinforcement. Maximum tension reinforcement. So for which you need to refer same clause, IS 456 2000, page number 47, same clause 26.5.1.1. So let me open the code. Yes, below the minimum reinforcement you have maximum reinforcement also. The maximum area of tension reinforcement shall not exceed 0.04 times BD. So it is 0.04 times BD. So it is 0.04 multiplied by width of the beam 200. Here it is overall depth. So overall depth it is 500. So 0.04 multiplied by 200 multiplied by 500. So it is 4000 mm square. So this is AST max. This is your maximum. So here you have three values. First one is AST provided. It is 830 mm square. Again you have AST minimum. Your minimum requirement is, I think it is 152 mm square. And AST max it is 4000 mm square. So if you observe these three values, the provided reinforcement area should be greater than the minimum and less than the maximum. Whatever the reinforcement you provided, it should be greater than minimum. So here 830, so which is greater than minimum 152 mm square, and less than the maximum, this 830 it should be less than maximum. What is the maximum value? 4000 mm square. So you can write like this. So this is AST minimum, this is AST provided, and this is AST maximum. So final comment is, provided reinforcement area should be greater than the minimum and less than the maximum. If the provided reinforcement which is less than the minimum, then you need to provide the minimum reinforcement only. Okay. So this is your IS 456 method. Next we shall discuss SP16 method. SP16 method. So it is very simple. Again, you have the same design stipulations: width of the beam, depth of the beam, FCK, Fy. You copy the same design stipulations. Same design stipulations. So same as above. Okay. So here first you calculate mu divided by BD square value. So your mu is analysis moment. I think it is 130 into 10 power 6 Newton millimeter divided by your width of the section 200 into your effective depth. So what is the new effective depth you calculated? I think it is this one, 445, because you are providing the reinforcement in 2 layers. So 445. So 445 square equals, so first let me calculate this value. So 130 into 10 power 6 divided by 200 into 445 square. So it will be 3.28. 3.28. So this is your mu by BD square value. So now you can refer SP16 page number 49 and table 3. So let me open SP16. So SP16, I think it is page number 49. So table 3, yes, table 3. First you read the heading: Flexure reinforcement percentage PT for singly reinforced sections. Here your grade of concrete 25 M25. So you have various grades of steel: 240, 250, 415, 480 and 500. So what is the mu divided by BD square value? It is 3.28. So your grade of concrete is M20, grade of steel it is Fe 500. So 3.28. So 3.28. I will take this 3.30. I will take this value 3.30 for mu by BD square 3.30. So your grade of steel 500. So it is 0.935. So PT it is 0.935. PT it is 0.935. It is for mu by BD square of 3.30. So I calculated the value of 3.28. Either you can interpolate. First you calculate the PT for 3.25 and you note down the values for 3.30 and you calculate the exact value for 3.28. 0.28. You can use linear interpolation. So here, instead of that, I have taken PT for 3.30. It is somewhat on higher side. So convert this PT to area of steel. So next, convert this percentage of steel PT to area of steel, AST. You have the formula. So AST equals PT multiplied by B multiplied by D divided by 100. So PT 0.935 multiplied by width of the section 200, effective depth I think it is 445, so divided by 100. So your AST it will be 0.935 multiplied by 200 multiplied by 445 divided by 100. So it is 832 mm square. It is when using SP16 method. So what is the AST when I am using IS456 method? Yes, it is 825. So while using IS456 method, so your area of steel AST it is 825 mm square. So there is a slight difference. So this is because of I have taken the PT for value of 3.30. So this PT 0.935, it is for a mu by BD square value of 3.30, but my actual mu by BD square is 3.28. It is somewhat on higher side. So this is how you can check SP16 method and IS456 methods. In the next class, we will take up design of doubly reinforced beams.